useful. Always if you have an idea of maybe coding a different bus speed, let's say 25. Do we have 25 megahertz?
24.
Yeah, 25 we don't have, right?
You could create one.
Yeah, let's say if you wanna do your 25, you can add it here, right? Now, before you just add like crazy, like 25 more configurations or 50 more configurations, always do this exercise. If you wanna add 25 megahertz, not gigahertz, megahertz, you could say, well, what happens if I do 1 over? Oh, this one gives me a cycle of 40 nanoseconds. So it seems like worth it, right? But if I decide to do 26 megahertz, I'm just gonna do 26 megahertz. Then you do 1 over, and it gives you this weird number for the cycle, then that's probably not worth it. Because it's gonna give you a cycle that is not good to work with. So you wanna have something, see what I'm saying? In fact, the ones I gave you here, some of them are not good, like the 32 megahertz.
Yeah, it kind of sucks.
Yeah, well, that one is not too bad, to be honest. That one is, the cycle is 31.25 nanoseconds. At least it's something that you can see, not a periodic number, right? 60 megahertz. That one gives me a weird number. See, 60 megahertz is probably something that I might ask you to do, but not really to work with. So in case you haven't noticed, I kind of like the 40 megahertz because it's a good number to work with. 64, I don't think it's that good either.
No, it's not.
But it's the maximum. That's why we needed to code this one. Because it's the maximum it can go.
So it's
No.
156.25.
We did discuss the flash latency thing. I think that's clear, and the instruction prefetch that needs to be added. But then when we discussed the GPIO settings, like Om did what I would expect everybody to do. Like kind of be curious and keep testing the things that I give you. And this is what I also said to the previous section. So you should at least run all my demos. So I'm going to make this very clear. To me, it's unacceptable that you guys, if you are not even running my demos, that is kind of unacceptable to me. Because if I'm making this whole thing of creating the demos repo inside as a submodule, so you can run my demos. If you don't even run my demos, what can I do? Now, if you cannot run them because of any configuration issue, you call me and I'll help you. But don't just say, oh no, you know what, the demos don't work for me, I'm not going to run them. No, because that's your opportunity to check things, right? And then moreover, you need to be curious about it. You need to say, well, what if I change this to the demo? What does it happen? So what Om started doing, he noticed that actually this low speed, high speed, very high speed, you needed to play with those configurations to be able to show the signals properly on the scope. He noticed, for example, that for the 40 megahertz, to be able to show the signal properly on the scope, it looks like you have to go to very high speed, not only high speed, right? And we kind of discovered that in class, and I said I have to revisit this. So when I give you the assignment, I'm probably going to give you a part when I ask you to explore that. But the main part is going to be with a common divider, let's say prescale by 16, to be able to show all the different clock speeds with the default configuration, which is very low speed. But be aware that if the pin is not able to be driven properly, like going all the way up and all the way down, and that's probably due to a speed setting. So make sure you code this one in your GPIO library. Okay? Any questions about that?
Just gotta get it done.
Yeah, but ask me for help, but do it. Don't just put it aside. Yeah, so I'll help you. But you need to do it. All right. Are we ready to move on? Because we're moving on to a new topic.
Let's do that.
Okay? Okay. So the new topic is not here yet, unfortunately, but I'm going to grab it from this other older section. I'm going to add that to the lessons very soon. But I'm going to start an intuitive approach first, because this is going to really help us home. Let's bring this one back. So we need to study the timers. What is a timer? Can anybody maybe describe in your own words what you think a timer is?
A value that measures the passing of time.
Okay. Valid description? Anyone else?
A
What do
value
you think a timer does?
tracks CPU clock cycles
Okay. By doing what?
by incrementing per
And
cycle,
that is the act of what?
counting.
Right? Yeah. So this is key for a timer. Counter. Timer is an independent counter. Okay? It's not like we did, see, if we go back to the exam, and this is where we're going. If we go back to the exam, which is not this one, we created a 5 microsecond tick sort of thing based on a delay, and then we were using a software counter to count how many of those we had. Okay? The timer is a peripheral that is
Hardware
able
timer.
to count on its own. So we don't have to be doing this. Okay? So the timer does have a counter. Is that clear? So if I don't tell you anything about this, I tell you, well, they can, you know, the micro has timers, they can count. What would be the obvious question you would ask?
How does it count?
How does it count? Like how fast does it count, right? How fast? Let's say I answer that question. What would be the following up question?
How do I implement it?
How do we implement it? But even before that, like you say, okay, if I tell you, you know what, this timer counts at microseconds, so it counts microseconds. What do you think you would ask me after that? Can it just count indefinitely, or?
What's the stopping condition?
Yeah. How many microseconds it can count? How many ticks, right? So those are very important questions. And they can all be configured. Okay? Now, how fast can the timer count? What do you think the default is? What is the default speed for the timer to count that? Hmm?
Milliseconds?
No, way faster than that.
Is it faster than nano?
But depends on something. What does it depend on?
Oh, your clock speed.
On your clock speed. Okay, let's say that I'm running at 40 megahertz. That's why I did this. 1 over gives me what? The times that it takes for one cycle. So at 40 megahertz, one cycle is 25 nanoseconds. So the timer at 40 megahertz counts at, so the tick time is 25 nanoseconds.
So that's our time base.
Is the actual bus speed. If I don't do anything, of course I can configure that. And I can change this. Can be adjusted. How? Using something that is called the prescaler. So basically there's a way to slow down the system clock so the timer can count at a slower rate. It could never count faster, but it could count slower. Okay? How many ticks? Well, in order to answer those questions, now we need to start looking at this guy. And this guy is the datasheet. When you go to the datasheet and you look for the functional overview, you expand this one. I'm showing it. Oh, I'm not showing it anyway. Sorry. Nobody said it. We go to the datasheet again. Go to the functional overview. We expand it and we look for timers. Where are they? Oh, they should be here. Timers and watchdogs. And we got this table that I'm going to put on the lesson. And this table is a summary of all the timers that the micro has, this particular micro. The table that we have on the older side, it has less timers because that little board, this one that you see here, had less timers. This one's got more. It has 2 low power timers that we probably are not going to deal with. It has the basic timers, which are very, very basic and simple to configure. We're going to work with this ones first. We're going to do a demo with these ones today. Then you have the general purpose timers. And then lastly, it has the advanced control timer that we're probably not going to use much. Okay. So if I ask you about the basic timers, which are timer 6 and timer 7, can anybody tell me how many ticks this timer can count based on the information that's on the table?
So it's 16 bit.
It's 16 bits. Okay, that's the answer. It's not the straight answer, but that's the on the right track answer, right? So the timer, if the timer is 16 bits, that means the range is from 0 to 2 to the power of 16 minus 1, which is 0 to 65,535. So what happens after the 65,535 tick?
Back to
Goes
0.
over. That's how the timers work. Okay? Just like in our digital logic course, when we're implementing a modulo 7 counter, it will count from 0 to 7 and then it will roll over. Okay? As you can see, almost like every single timer is 16 bits. There's only one timer that is 32 bits. So this one can count like super large numbers. Okay? So the other ones will count 65,535. So now that I know this, I can basically grab any timer. I can configure the prescaler to make the timer tick at a certain rate that is easy to work with. What is the one I suggest? I like this one, 1 microsecond, because it's easy to work with. Let's make the timer tick at 1 microsecond. So then it's going to count around 65 milliseconds max. Okay? Easy to work with. Okay. If I am running at 40 megahertz, what is the prescale I need to be able to tick at 1 microsecond?
4.
4?
Hold on.
Almost. Close, but not quite. So if I divide this frequency by 4,
It's 10
then it's going to be 10 megahertz. So the tick is going to be
Oh, it's 10.
0.1 microsecond.
It's 10, right?
It's 4 times 10.
Yeah.
So I need to prescale by 40. Why? Because if I divide the clock by 40, then the result is going to be 1 megahertz, and 1 megahertz is 1 microsecond. Right? Yeah. 1 megahertz is 1 exponent 6. 1 micro is 1 exponent negative 6. Right? All the way? This is simple math, guys. So, if we're not following this, we need to go back to math. Unfortunately. Yeah. Engineering notation. All right. So, we kind of have an idea of how to prescale. Now, that happens in some PSC register. We're gonna do this step by step. There's another register that is very convenient that is called the ARR register, and it stands for Auto Reload Register. And it's convenient, why? Because you may say, you know what? I don't want this timer to count all the way up to 65 by 35. I want to make it a modulus 1000 count. Then to make it a modulus 1000, what is the maximum number in a modulus 1000 count?
6.
The maximum number that it can count up to. Modulus 1000.
Oh, 65 and change.
Okay, a modulus 8 counter.
So yeah, 999.
9999, yeah. Modulus 1000 means from 0 to 9999. I just want to make clear that when you want 1000 ticks, you need to write a 9999 here. Sorry, 999. Because the 0 is included. Because when the timer rolls over, that is 1000. Okay? Same thing for the prescaler. Questions? Now, in the lesson I have from last term, that is going to be tweaked so we can convert it into the lesson for this term. We have here a bunch of stuff in a different table, see? But the part that I want to maybe focus on in this part here. It says that basically with a timer, we can generate 3 types of events. Okay? The most basic event is the update event. And that happens basically when the timer rolls over. So if I'm counting all the range up to 65, 5, 35, when it rolls over, that update event happens. That's the easiest thing we can do with a timer. And that's the first one we're going to do. Or whatever value we put in the ARR. But there's some other modes that are called output compare and input capture. And in this output compare, it comes with what we know as PWM. We will study all that, but later. Those use the capture compare registers. And that basically compares those against the counter, and they generate events when the counter equals that number. Okay? Or when you feed a signal as well. But that's more advanced. Now this thing, going back to this table, in order to understand all that, we know the resolution of the timer. We also know, by the way, if the timer, most of the timers, or half of the timers will count up. But some others can be configured to count down or up down. So basically going from 0 to this number and then down, if you wanted to. But in most cases, we're just going to make the timer count up to make it simple. But we have this other column that says how many capture compare channels the timer has. And those capture compare channels have to do with other applications like output compare and input capture. And as you can see, timer 16 and 17 have one of those. Timer 14 also has one of those. Timer 15 has 2, and the other ones have 4. So meaning that if you wanted to generate PWM signals, you could, with one timer, generate 4 of them using these output compare registers. That is material for later. For now, we're going to start with these basic timers that have how many capture compare registers?
None.
0. Yeah, none. So that means that we cannot do anything else with those timers other than the update event. So the only valid event that we can use with those basic timers is this guy, which is why we're going to use that one first. Okay? So, if we go to the set of steps here, obviously when we work with the basic timers, the steps come to a very short list. Because step 1, we have to do it. That's where we set the prescaler, right? That's where we say, hey, if we're at this frequency, we're going to prescale by whatever to tick at this. Then in the auto reload register, we're going to say, hey, we're going to make this timer modulus whatever we want. Done. Then configure the capture compare register. Not now, because that's for later. Interrupt if required. Not now. That's for later. PWM mode. Not now. That's for later. Enable capture compare channel. This one doesn't have any capture compare channels. For later. Enable counter timer. Yes, it needs to enable it to start counting. So for these basic timers, we only have to configure this, and that. And that's it. Okay? All right, so let's turn on the other projector, and I'm gonna have to erase this so it doesn't look too messy, so we can look at the steps. Okay, so I did create a demo. I think that's already pushed. But without looking at the demo, this demo is going to use timer 6, because timer 6 and timer 7 are the basic ones, okay? Based on what we know so far up to this point, what do you think is the first thing we're going to do before we even start using this timer? Hmm?
Enable the timer clock.
Yeah, enable the timer, so connect it to the RCC, right? Excellent. So where is that? Here. Timer 6 gets enabled in the APB ENR1. And probably timer 7 is also here, but not all the timers are in this group. Remember, there's also an APB ENR2. So you need to make sure you find the mask. Okay, enable it there. And then after that, we got the clock at 40 megahertz, just like the other demo, blah, blah, blah. Latency output, we're gonna leave it the same for now. The second USARTs, leave it the same, yeah.
I'm actually just wondering if anybody else has access to this. I went to go do a poll and I'm only up to demo 22, so.
Oh, to this demo?
Yes, sir.
I forgot to push, maybe. Oh, yeah, I haven't pushed.
Oh,
Sorry.
God.
Yeah, but good that you asked. Let's just push it. Okay, it's pushed. I might insert some modifications, but. Okay, the timer configuration starts here. So first thing, I want to set the timer to tick at 1 microsecond, okay? So that means I want to prescale by 40. Why by 40? Because I'm running at 40 megahertz. If I was running at 64 megahertz, then I want to prescale by 64 to make it tick at 1 microsecond. Let's take a look at this prescaler register. The timer 6 and 7 are together in chapter 23. Timers that are exactly the same, they're usually grouped in the same chapter. So timers 6 and 7 are the basic timers, and they are here, and the registers are here. So the prescaler is which register? This one here. The prescaler is a 16-bit number from 0 to 15, so you can put any number there from 0 to 65,535. The default is 0, which means what? Prescaling by how much? Prescaling by 0?
There is no prescale.
Yeah, prescaling, 0 means no prescale, so basically prescaling by 1, okay? Yeah, because you cannot really divide by 0 the frequency. That's why putting a 0 means 1, which is why in my prescale, I'm doing 40 minus 1. I want to make clear that I'm prescaling by 40, but I'm subtracting 1 because that's the way it works with the prescaler. Right? It's always minus 1. Okay? Then, second step is to set the auto reload. If I don't set it, the auto reload register, this one here, the ARR, is going to be by default FFFF in hex, which means the maximum they can count up in 16 bits. So 65,535. But right now I want to make it a modulus 200. So I'm going to say 200 minus 1, because that's how a modulus works. It's always minus 1. And then the third step, I enable the counter. And that happens in the control register 1. Counter enable is right here. Is the least significant bit. Counter enable. That means the timer now started counting. Questions up to this point?
Got one.
3 configurations only for the basic timer. Prescaler, auto reload register, enable counter.
And the auto reload register is what allows us to
Is to say how many ticks you want before you can generate an event. That's basically it. It allows flexibility, because otherwise we'll be stuck with the 65535, and then we'll have to work only with the prescaler. Now in this case, we could use the prescaler and the ARR together.
What if you want it to be like 5 milliseconds?
If you want it to be 5 milliseconds, then 5 milliseconds is actually 5,000 microseconds. So all you need to do is just put a 5,000 here. Right?
Oh, that's not.
Yeah, modules, yeah. For now, I'm gonna make it 200 because I wanna make something like very short time, right? But you could do 5 milliseconds. Of course, the maximum you could do is 65,535, right? Otherwise, then you have to change the prescaler at that point. Any other question?
and then this is just a
Okay. How is the software going to be aware when the timer count is up, basically when it rolls over? How do you think is that going to happen? Without looking at the code, because that's why we didn't want to push yet, because if you look at the code, you see the answer, but I want you guys to think a little bit about it. Remember when I talked about the type of registers that we have in the micro?
Mm-hmm.
We have control registers. The control registers are to configure the peripheral in a certain way, and then we let it be. That's exactly what we're doing here. These 3 are control registers. Even though this is not called CR, but it is a control register because we only set it once, and then we let it go.
And the question asked was, how does the
Yeah.
software?
Yeah, I'm gonna get to that point. Then the second one, or the third one, but I'm gonna skip the second one, so let's see if you guys remember. The third type of register that we have is the data registers. These registers are for transferring data. When you use your USART, you write to the data register. When you read from the data register, and that's how the data gets transferred, right, through those registers. What was the second type of registers that I talked about?
Registers.
How does the peripheral communicate with the software? How can the software know what's going on with the peripheral?
By checking the state.
Checking the status registers. Excellent. Status. So the status registers contain flags. Okay? So how are we going to know when the update event happens? How are we going to know when the timer rolls over? There's going to be a flag that gets activated in the status register. Let's take a look at the status register. We only have one.
Enablement.
Is the SR. Oh, that's going to be difficult. We have so many flags here. We only have one flag. There's no way to go wrong here. We just need to check for the update flag.
Okay.
That's it. We're going to mask that flag. That is going to tell us that the time is up. Let's read through this. Update interrupt flag. This bit is set by hardware on an update event. The update event happens when the timer rolls over. It is cleared by software. 0 means no update occurred. 1 means update interrupt pending. This bit is set by hardware when the registers are updated. Well, then it's more about that. So basically, we're going to do this. We're going to say, well, if the update flag is set, what do? We toggle an LED, but we clear the flag.
So timer 6 pointing to the status register.
Yeah, we're masking the flag to see if it's active. Okay, so why is it important to clear the flag? Well, it says that it's cleared by software, because let's say the timer is going to start from 0, it reaches 9999, rolls over, is gonna set that flag, and then if you don't clear it, the timer is gonna keep counting, but the flag is gonna remain set. So then you're gonna keep going here, here, and here. So this is gonna toggle like crazy. That's why you need to clear the flag. We're looking to the blocking approach in just a moment. We're just testing this one first. We're gonna run this code. And we're gonna show you the camera. And that happens exactly more or less at 200 microseconds. That's it.
So that's our debug, essentially.
Yeah, that's our testing. Now, if I forget to clear the flag, this is what happens. Now the pin is going to toggle as fast as it can, which is 1.2 microseconds. Why? Because we forgot to clear the flag. So clearing the flag is important. To answer Carl's question, he said, what if I want 5 milliseconds instead? Well, 5 milliseconds is 5,000 microseconds. Since this timer is ticking at microseconds, it's so easy to configure. I just need to write a 5,000 there. Now, if I run it, obviously this is way longer time, and it's exactly 5 milliseconds. Oh, more or less. There's a bit of an inaccuracy there, maybe because of the oscillator, but we can look into that later. So see why I said don't worry about the delay 1 millisecond or whatever thing that you were coming up with. It's not going to be important now because now we have the timer. Now, can anybody explain to me why is this approach non-blocking? Why do I call it non-blocking?
Because there's no delay.
There's no delay. If the flag is not active, it's just going to loop through, right, and keep going. So you can add more lines to that code after, and they're going to be executed anyway. Okay? Whereas these would be the blocking approach. The blocking approach says, hey, you know what? While the flag is not active, I'm just going to wait here on this line and do nothing. Then when I'm past this line, I'm going to clear the flag and I'm going to toggle the LED. The results is going to be more or less exactly the same. Let's give it a try and take a look at the scope. Well, right now we're back to the 200s, right? So, and it's about the same thing. Now, why is the non-blocking better than the blocking?
We can just write our code, and then when the timer is at a certain value, we can execute a portion of that code,
Yeah.
and we don't have to work around a particular time
Yeah.
slice.
Yeah, exactly. If I block the code for 200 microseconds, if I need anything to happen at a faster than 200 microsecond rate, then it won't happen because this thing is blocking there, right? That is the issue with the blocking, which is why in the exam, if I ask you to do 500 microsecond events manually, right, with those delay cycles, whatever, I couldn't ask you to run anything faster than that because it was not possible. And which is why I said that in order for the exam to work together, you couldn't insert millisecond delays on top of the 500 because that's not the way it was going to work. Because it was going to add more blocking time. Okay? Questions? Yep.
Why would we want to introduce a blocking delay when timers are available?
Yeah, well, with the timers you can do both. Actually, you could create a non-blocking delay function and a blocking delay, and I'm going to give you some pointers in terms of how to write those functions if you are interested in writing them. In general, I would say blocking delays are discouraged. I do not recommend blocking delays at all. However, they are necessary in certain situations. For example, the typical one is initializing an LCD. An LCD requires certain steps, and since LCDs are very slow, they say, okay, send this command, now wait for 20 milliseconds. So you cannot do anything during that time because you're initializing the LCD. You have to block the code there and wait for the initialization sequence. That's one of the cases where you want that.
Some of them are very slow to turn on,
Yeah.
like multiple seconds.
Yeah, in some other cases, you can, in any case, you could always go around with the non-blocking, because the problem is that the non-blocking, it may make it more complicated in terms of how you implement the code. Because for example, you can just use the non-blocking and somehow when the 100 milliseconds are due to whatever method that you use, then you can sort of like have a callback function that gets called, right? But that makes it more complicated. Sometimes it's just better to block the code there, so it's easier, okay? But in general, blocking code is not good. So we're gonna try to stick to the non-blocking. Any other question? Now, using these timers is very simple, right? So it doesn't require a lot of effort to get it working. Now, of course, we haven't yet discussed something that is called interrupts that I plan on discussing at the end of this course, although officially it's not part of this course, but I like to discuss it because I feel like when you arrive to 2250, if you don't know interrupts, it make everything slower. So it's better just to know. When we discuss interrupts at the end of this course, because you guys have already seen events, right?
Yeah.
In 16, so you should be familiarized with the concept of, asynchronous events. So we're going to revisit the timers, and that's going to happen very soon. It's probably going to happen next week that I start talking about interrupts. Now, how could you do this with this timer with interrupts, for example, instead of, because there's a problem with this. There's a bit of a problem. Because this is non-blocking, but this method is still what we know as polling. So basically, the system is polling the flag. It's trying to see if the flag is active. And there's a bit of a problem with that, because that depends on how fast is this code running. If I start adding more lines of code, even though this thing is non-blocking, is going to be limited by the time that it takes to execute the loop, right? And when I talk about this, I always give this example. Let's say that you're working on an assignment, and I come every 10 minutes to check if you're done, right? So then I come to you and I say, are you done? You say, no. Go for 10 minutes, I want to have a look. I come back again and say, are you done? No. I go, and then it happens that 1 minute after that, you're done. But then I don't come back to you the next 10 minutes. So basically you wasted 9 minutes that you were done, and I didn't know, because I didn't check. That's what polling is. How would that be different? If you raise your hand when you're done, you basically interrupt me from whatever I'm doing, so I can service and go, okay, you're done. That's an interrupt. That is different. So there's a way for these guys to actually trigger an interrupt, so this can happen automatically, but then we have to add more code, and we're gonna study that probably maybe next class.
Is that just like initializing a flag, and then when the flag is ready, it's just like.
Well, that's why this flag is called the interrupt flag, because actually, if you enable the interrupt, which is already in the lesson, right? It says that you have to enable it here. In this DR register, see? Enable the interrupt is if required. So if you require the interrupt, then you need to enable a flag here in this register, and that will trigger an ISR. But an ISR, guess what? Interrupt service routine. It's just like an event handler. It's a specific function that you need to code. And we need to discuss a few things before we can get there. For now, we're just saying that we can pull this flag for now, and things are gonna more or less work, although the ideal scenario is gonna be the interrupt. And the same thing with the USARTs. When we discuss interrupts, we're gonna go back to the USARTs, and then we're going to revisit the USART, because there are cases where the USART could also lose characters, because when you're checking for a receive byte here, you're always doing polling as well. You're not doing ISR. Questions about this?
Not sure what to even ask.
Huh?
Not sure what to even ask.
No? Did you guys have an exam that everyone looks like so drained and tired? It's only Monday.
To make a lot of assignments that were due
Oh, okay.
over the weekend, depending on the classes you're taking.
All right. Well, I would say work on the USART after this assignment. I could do some checkups if you're ready. I gotta push the clock assignment, and there's a lab coming for that too. So you guys have enough to work. And timers, we're just starting, so probably by the end of this week, we're gonna have an assignment for timers. For now, I just wanted to show you that the simplest way to use a timer is just using the update flag. But this is just scratching the surface. There's way more that we can do with the timer. And we're going to do other activities where, guess what? We're gonna get to use those protoboards again to drive the speaker. So that's gonna be fun. So we're gonna need a BJT transistor in jumper wires. Any more questions? No? Okay, maybe as an exercise, try to see if you can, because you still have access to the exam, take a copy of the exam and try to solve it using timer now. See how that would be different. Instead of having that delay microsecond, you can now generate a 500 microsecond event with the timer easily.